In this video, I want to talk about one-to-one, onto, and bijective functions. And in particular, I want to talk about how these notions apply to linear transformations. I'm going to start this video with a review of what it means for functions to be one-to-one, onto, and bijective when we're talking about real valued functions. That is, functions whose inputs are real numbers and whose outputs are real numbers. Now, if you feel comfortable with what it means for a function to be one-to-one, onto, or bijective, you could definitely skip ahead to where I talk about linear transformations. But if you want a review of this, or if you're not familiar with these terms at all, I recommend watching the first part. Okay, so we're going to do a lot of graphing here because we want just visual understandings. What does this mean for functions to have these properties? So we say that a function, and again, we're talking real valued functions here. So if a function takes real inputs and gives you real outputs, we call this function one-to-one, which we often abbreviate one-to-one, like this. And we often call this, or another word for this, I guess, is injective. If you hear the term injective, it's just a fancy word for one-to-one. If each output value or each, let's phrase this differently. If each real number is the output or at most one input, in other words, there aren't two different values that can give you the same output. And let's look at an example here. So this example here is the function f of x equals e to the x. Yeah, we don't need to cram ourselves this much. This function f of x equals e to the x is one-to-one because we can't get the same output for two different inputs. Different x values that we plug into the function e to the x always give us different y values. Graphically, this is often referred to or described in terms of the horizontal line test. If I draw a horizontal line through this graph, it will intersect the graph in at most one spot. It doesn't intersect it twice. Now, it doesn't always intersect the graph, right? If I drew a horizontal line below the x-axis, that's not going to hit this graph. But every horizontal line will hit this graph at most once. All right, let's look at a different example. What does it mean for a function to be onto? I'll use a different function name just so that we can refer to these functions later. Function is onto. Another word for onto, if you hear this, surjective. Surjective means the same thing as onto. If each real number is the output or at least one input. So every real number appears as the output for at least one input, maybe more than one. And for this one, I'll do an example. We'll get rid of e to the x. We'll talk about later whether that's onto. We'll look at this function here in blue that I'll call g of x. Wasn't scrolled down to read this. So g of x is onto if each real number is the output for at least one input. This example, g of x equals x cubed minus 4x plus 5. Now, these cubic functions, you're hopefully familiar with them. They kind of go off to infinity in each direction. And this one goes off to positive infinity as we move to the right and negative infinity as we move to the left. And so every possible y value appears as an output. The way we describe this is in terms of another horizontal line test often. We say that, look, if we draw a horizontal line, it will always cross this graph at least once. All right, so we have 1 to 1. We get an output for at most one input. Onto, we get an output for at least one input. And then a bijective function. Here I'll actually remember to scroll down to a new spot. We'll call this h. We have a function h from the real numbers to the real numbers is bijective, or in other words, h is a bijection. If, well, we already had at least and at most, and now we're going to have exactly. If each real number is the output for exactly one input. And the example I want to look at here, I think this one's in green. So let's move to a place where we can see this a little better. This is an example of a bijection. And I'm calling this h. This is the function sine x plus x. So this is a bijection. And what this says in terms of horizontal lines is that if I draw a horizontal line across this graph, it will always cross this graph exactly once. It won't cross in two spots. One final thing to point out is that being a bijection, having each real number be the output for exactly one input, that's the same as having both of these other two properties. That is, if a function is injective and, 1 to 1, and it's onto or surjective, that means it has at least one and at most one input gives you each output. That means it's a bijection. So in other words, a function is a bijection if it is 1 to 1 and onto. So 1 to 1 and onto is exactly the same as being a bijection. So in some sense, when we're talking about 1 to 1 onto and bijection, we're really only talking about two properties, 1 to 1 and onto, and being a bijection is just having both of those properties at the same time. So as we go back through our functions, let's kind of recap this. This function f of x e to the x, this is 1 to 1, but it's not onto. You can never get negative outputs. So we have a function that's 1 to 1, but not onto. This function f of x equals x cubed minus 4x plus 5, this is onto. You get every single real value as an output, but it's not 1 to 1. You can see in this graph that, for instance, y equals 5 has 3 possible values, and actually by looking at the function, you can see what those values are. Right? If we plug in 0, if we plug in 2 or negative 2, we'll always get 5. So we have 3 values that give us 5. So this thing is not 1 to 1. So this is a function that is onto but not 1 to 1. We then saw an example of a function that was 1 to 1 and onto, or in other words, a bijection or bijective. That was this function h of x equals sine x plus x. And finally, there's one more combination of these things that we haven't looked at. Can we have functions that are neither 1 to 1 nor onto? And we can. Here's a really simple example. So I'll draw this in purple. So this example I'll call, I don't know, k of x, which is x squared plus 3x minus 2. This function is not 1 to 1 and it's not onto. So it's definitely not a bijection, right? We can see that it's not 1 to 1. There are multiple values that give us 0, multiple x values. It's not onto. There are no x values that give us negative 5 or negative 10, for instance. And so it's definitely not a bijection as well. And when we're dealing with real numbers, it's usually hard to figure out whether a function is one-to-one, onto, or bijective. I gave you examples where we just graphed them and we kind of trusted that the graph was telling us the right thing about the function. But as a general rule, there's not some straightforward process given the equation of a function to know whether it's one-to-one, onto, or bijective. As we move to linear transformations, what we're going to see is that things work out really nicely. Generally speaking, we can define one-to-one, onto, and bijective for any sort of function, right? If you look at these definitions, you can convince yourself that these definitions don't actually have anything to do with the fact that our input and output are real numbers. Right? A function being one-to-one is just saying that your possible outputs appear for at most one input. A function being onto says that all of your possible outputs appear for at least one input. And a function being bijective is saying that all of your possible outputs occur for exactly one input. And so these properties are not really dependent on working with the real numbers. They're properties that have to do with outputs and inputs of functions. And so when we start talking about vector spaces and linear transformations, these definitions translate over nicely. And what we're going to see in this video, and what the main point of the video is, that unlike with real valued functions or lots of other situations, there is a very straightforward algorithmic way given a linear transformation to figure out, is it one-to-one, is it onto, is it a bijection? So let's look at that. So this is the process given a linear transformation for determining if it's one-to-one, onto, and or bijective. And I'll go through this with a series of examples. First, we're going to check some easy things. That is, there will be some things that we can check without any calculations that will allow us to know whether a linear transformation just can't have one of these properties. We can rule out certain situations pretty quickly. If not, so if we can't rule out that a linear transformation is, for instance, onto, we'll have a process that involves converting the matrix into echelon form and figuring out where there are pivots. At this point, this shouldn't be a shock to you. It seems like everything we do, for the most part, we can accomplish by converting a matrix into some sort of echelon form, and often what we're interested in is pivots. And so let's go through this by example, because this is kind of a long list. So let's start with our first example. All right, so here I have a linear transformation from R3 to R3, and I've defined it by matrix multiplication. This is one of the standard ways of defining a linear transformation. I just tell you what the matrix of the transformation is. It's a transformation from R3 to R3, and we want to know, is this one-to-one, is it onto, and is it bijective? And of course, the answer to the first two questions will tell us the answer to the third question. Let's go back to our list. So let's start by checking the easy things. So here we have a linear transformation from R3 to R3. And these three easy possibilities, we're checking, look, is the output dimension space lower dimension than the input space? Well, that's not the case. They're the same dimension. Is the output dimension greater than the input dimension? Well, that's not true either. And then this third condition, it cannot be bijective unless the output and the input have the same dimension. None of the easy things apply here. So our first example, we're not going to have any of these easy properties we can deal with. We're going to have to hop right into the harder situation. Okay, so the first thing we're going to do is find the matrix of the transformation. Now, we were given the matrix of the transformation, so we're great. We're already done with that, but we'll see in later examples, sometimes we don't start with the matrix of the transformation. Okay, our next step is to convert the matrix to echelon form. So let's do that before we even look at the list below. So I want to convert this matrix A to echelon form. Here's our matrix, and we're going to convert it to echelon form. And as I often do, I'm not going to write out all of the row operations. At this point, we should believe that we can do a series of row operations to convert this thing to echelon form. And as I do these row operations, I get to this, at some point, I get to this matrix. And if you are trying this problem on your own, you might get to a different matrix in echelon form because there are lots of different equivalent matrices in echelon form, right? I didn't go all the way to reduced row echelon form because I'm not going to need that. The important thing is going to be where are the pivots. And so if you did this on your own, you might end up with a different matrix, but if you did it right, you're going to end up with the same pivots. And these pivots are going to allow us to figure out whether this thing is one-to-one, bijective, and or onto. I don't know why I said it in that order. All right, so what do we check? If there is a pivot in every column, the transformation is one-to-one. Well, there is a pivot in every column. So this transformation is one-to-one. If there is a pivot in every row, the transformation is onto. There is a pivot in every row. Back there yet? So this transformation is onto, and we already know the answer to the next question, but if there's a pivot in every row and every column, which there is, we just checked, the transformation is a bijection. So this is both one-to-one and onto, and therefore T is a bijection. All right, example 1 is taken care of. Let's move on to another example. And again, with this second example, we're going to be given a linear transformation defined in terms of its matrix multiplication. So this is a linear transformation from R4 to R3. But since we have different dimension input and output spaces, we're going to be able to rule out one of the possible properties. So let's see what that is. All right, so if the output dimension is less than the input dimension, it can't be one-to-one. The output is greater than the input dimension, we can't be onto. So in this example, we're going from R4 to R3. So N is 4 and M is 3. And so we are in this top situation here. This transformation cannot be one-to-one because we're going from R4 to R3, and 3 is less than 4. So immediately, we know that this is not one-to-one. So let's write that down. All right, so we didn't have to do any calculation there. Now, we can also rule out, once it's not one-to-one, we already knew this, but going back to the video overview, it can't be bijective because the dimensions of the input and output space are not the same. And so it's definitely not a bijection, but we still need to actually check whether it's onto, because it could be onto. When we have a situation where we're going from a larger dimension to a smaller dimension, we can't rule out the possibility that it's onto. And so we have to follow the same process. And so I'm not going to flip back to the overview page to do this. I'm going to just work it out here. What we want to do is we want to take this matrix. We want to convert it. That's not what I wanted to do. Let's get rid of this thing. Didn't copy well. We want to take this matrix. We want to convert it into echelon form. Using a series of row operations, or maybe we'd use a computer or something like that. And when I apply these row operations, I eventually get to a matrix in echelon form. Like this. And again, if you're doing this on your own and you're trying to check on your own that you can do these things, you might end up with a different matrix, but you'll end up with the same pivots. These are the two pivots. There's only two pivots here. And we're trying to check if it's onto So we have to check, is there a pivot in every row? And there's not. So there's no pivot in the third row. So S is not onto. So S doesn't have any of these properties. It's not one-to-one or onto, and so it's definitely not a bijection. And also, we could have figured out, if we wanted to check that S is not one-to-one, we can see, yeah, we only have a pivot in 2 of the columns. We don't have a pivot in every column, and it's not a bijection because you would need a pivot in every row and every column. All right, let's move along to another example. I know this is a lot of examples, but I think it's useful to see some of the details that can happen. Now here we're working with a linear transformation from R2 to R3, and we're not given the matrix of the transformation. We're just told that the transformation is linear, and we're told where it sends a basis of the input space, R2. And we want to determine, is this one-to-one, is this onto, is it a bijection? Okay, so I'm not going to keep flipping back to the video overview screen, although I guess I'll give you a chance. I'll flip there for a second. You can pause the video if you want and see if you can think about how this is going to apply here. But the first thing we check is the easy things. This linear transformation cannot be onto and it cannot be a bijection. So we're going from a smaller dimension space to a larger dimension space. So we cannot have an onto function and we cannot have a bijection, but it might be one-to-one. So since our input is less than our output in dimension, H is not onto or bijective. You'll start to see this pattern. If we can rule out either one-to-one or onto, then we've ruled out bijection, right? The only situation in which we could have a bijection is when the dimensions are the same, in which case we can't rule anything out to start. But we still need to check, is it one-to-one? And this is where we actually need this step in the video overview. So I lied. I will go back to the video overview screen. We don't have the matrix of the linear transformation. So we need to find the matrix of the transformation before we can figure out if this transformation is one-to-one. Now you may remember this transformation, or maybe not. This is the same transformation that I worked with in the calculations with linear transformations video. I called it T in that case. But if you want to see where this comes from, go back to that video. I go through the computation of how do we figure out what the matrix of this is. And if you can't remember how to do that, I recommend going back to that video. But the matrix that we found, let's make sure I get this right, is -3, 5, -1, 1, 7, 6. And in reduced row echelon form, because I've given you examples where we went just to echelon form because that's all that we need, but there's not a harm in going all the way to reduced row echelon form, in particular if you're using a computer to do this. None of these matrices are giant, and you're not really wasting any time by converting all the way to reduced row echelon form. We get this matrix. And looking at this matrix, we're interested in whether this is a one-to-one function. We have our pivots. Let's highlight our pivots. We have a pivot in each column. So H is one-to-one. So H is an example of a linear transformation that's one-to-one, but it's not onto, and therefore not a bijection. There's one more example. Again, I know this is a lot of examples, but I think that we want to see a lot of different possibilities. And in this example, we're going to have a similar situation where we have to do something first. So here I'm given a linear transformation from R3 to R2. And it's defined in terms of where it sends a vector based on its entries. So I'm telling you, look, if you have this vector in R3, create a new vector in R2 by combining the entries in this specified fashion. I'll point out, it's not really even clear. I mean, this is a function, right? This definitely tells you if you have a vector, you can figure out what vector it gets sent to. But it's not maybe clear that this is even a linear transformation. And so I'd recommend if you want, pause the video or do this later, try to convince yourself that this is a linear transformation. That is that it respects addition and scalar multiplication. Okay, so we're gonna first approach the easy questions. This is going from a higher dimension space to a lower dimension space. And so since our output dimension is less than our input dimension, K is not one-to-one or bijective. We can immediately rule those out. But we can never rule out everything, right? Our easy options never allow us to rule out everything based on the dimension. We actually have to check if it's onto. And again, we're going to need to find the matrix of this transformation. And so how do we find the matrix of K? We have to figure out where it sends all of the standard basis vectors. And it actually is not too bad. This might be a hard thing to figure out, but once we realize what we're supposed to do, where does 1, 0, 0 go? Well, it's A is 1, C is 0, B is 0, C is 0. So K of 1, 0, 0 is 1, 0. And similarly, K of 0, 1, 0, if we plug in the second standard basis, we're going to get, by the same process, 0, 1. And finally, if we plug in the third standard basis vector, we get 1, 1. And so the matrix of K is where the first standard basis goes, where the second standard basis goes, where the third standard basis vector goes. So this is the matrix of our linear transformation. And actually, once you write out this matrix, you should convince yourself that you realize that this matrix does do exactly this. That is, any vector you multiply by that matrix gives you the output in this form. And so that's a way of thinking about this being a linear transformation. Okay, we're actually even though we had to do all that work, we don't have to do any more work because this is already in echelon form. It's already in reduced row echelon form, which doesn't really matter, but we know where the pivots are. This matrix has a pivot in each row. And so K is onto. So to recap, we have this process for figuring out whether a linear transformation is one-to-one, onto, or bijective. And this is actually kind of an amazing thing that it's so easy to do because, as I mentioned in the part about real valued functions, one-to-one, onto, and bijection are not things that, or are things we can define in any situation where we're talking about functions, but are not things that in general are easy to determine. Usually we have to take what are known as ad hoc approaches, where for each function we're considering, we have to think about how we're going to show that it's one-to-one, onto, or bijective. There are strategies, but it's not usually this easy. So for linear transformations, the first thing we do is we check the easy things. We look at the dimensions of our input and output spaces. If the dimensions are the same, if m equals n, we can't rule out anything. It could be onto, it could be one-to-one, it could be a bijection. If the dimensions are different, if either our input is bigger than our output in dimension or our input is smaller than our output in dimension, then we can rule out two of the possibilities, right? We can rule out one-to-one and bijective, or we can rule out onto and bijective. But regardless, if we're trying to figure this out, something will be possible, right? We can't rule everything out. And so once we get there, we have to find the matrix of the linear transformation if we don't already have it. We have to convert this to echelon form. That could be reduced row echelon form, but it's not necessary or helpful. And then we check where the pivots are. There's a pivot in every column. We have a one-to-one transformation. If there's a pivot in every row, the transformation is onto. And if we have a pivot in every row and every column, the transformation is a bijection. And finally, before I kind of dive into the why this is true, which you can skip if you want, I just want to point out we have shown examples of all four possibilities. So in example 1, we had a bijection, one-to-one and onto. In example 2, we had none of the properties. We had not one-to-one or onto, and so definitely not a bijection. In example 3, we had something that was one-to-one, but not onto, and so not bijective. And in example 4, we had something that was onto, but not one-to-one, and therefore not bijective. So all four possible combinations of these properties do exist with linear transformations. All right, now is the part where I go into the why this works, which, as I always say, you can skip if you want. If you're just here to do the problems and to figure out how to do that, that's fine. But I think there's value in watching this sort of thing at least once. The first thing I want to point out is that the easy things follow from the hard things. What this means is these, if you think about checking where there are pivots, this tells you that these properties have to be true. So let's go to an example. Like if I'm looking at example 2, I don't need to do any calculations to tell you that when I convert this into echelon form, there will not be a pivot in every column. Because there can only be 3 pivots at most. As it turns out, there are 2, right? But there couldn't be more than 3 pivots because you can't have more than 1 pivot per row. And so I can just look at this matrix and say, this does not have a pivot in every column. This cannot be one-to-one. It cannot be a bijection. And this is all about matrix dimensions, right? And so the number of rows of a matrix is the dimension of the output. The number of columns of a matrix is the dimension of the input. And so that's why dimension of input and output allow us to rule things out really quickly. Or one way of thinking about it is that those harder properties, where there are pivots, whether there's a pivot in each row and each column, you can rule some of those out sometimes based on the size of the matrix. All right, so that's why the easy things work. But why do the hard things work? And I think this explanation, well, hopefully I do a good job of this explanation. I make no claims that my explanation is going to be good. But if I were to explain this well, I think this is a really nice application of using linear systems and their connections to everything in linear algebra to understand why things are true of other linear algebra situations. So what I mean by that. So we have, let's use an example. So I'm trying to see, let's just go to an example where we have space. Let's do the one-to-one example first. So I'm trying to see if this transformation H is one-to-one. So my question is H one-to-one? Another way of saying this is if I call this matrix A, or I've used A and B, let's not repeat. If I call this matrix C, I'm really asking, is it possible for C times V equals B to have multiple solutions? Because this would be saying that you have 2 values that you can plug into H to get B as your output. That's really what we're asking. Because if it is possible, then this is not one-to-one. But if it's impossible for that to happen, then it is one-to-one. And so how would we do this? Well, we would take this matrix and we would say, okay, well, let's set up what that would mean. That would mean that we're solving the linear system with this augmented matrix. And I'll just put lines here saying this could be anything. We're trying to determine, will this have multiple solutions? Is there some vector B where this will have multiple solutions? These could be anything. And what we determine is that we convert this to reduced row echelon form in our process of solving. And as I said, we get this matrix on the left. And who knows what we got on the right? We got some stuff, right? Maybe I don't like these lines. I'll put like asterisks, right? So an asterisk is just indicating that we don't know what these values are. This is something, right? And we get something here. And what we realize by looking at this is that the answer is no. It can't have multiple solutions. It might have no solutions, right? If we end up with something here that's non-zero, then we have an inconsistent system, but that's fine, right? That doesn't affect it being one-to-one. But it can't have multiple solutions because there are no free variables. Or in other words, there's a pivot in every column. Because we have a pivot in every column in echelon form, it means that when we solve this system for any values in place of these asterisks, is that how you pluralize asterisk? I don't know. When we solve this, you don't get free variables, and so you can't have multiple solutions. You could have one solution if you get a 0 here, or you could have no solutions if you get non-zero here, but you can't have multiple solutions. And so this means that H is one-to-one. So that's why checking the columns tells us whether it's one-to-one. What we're really checking is, are there free variables when we solve this linear system? Let's do the same thing here. Where we're trying to see if this thing is onto. We're trying to check if K is onto. Another way of asking that, so let's call this matrix D, is there always a solution to something like D times V equals B? Or in other words, if we draw this augmented matrix, and we're not really sure what's going in the right-hand side, do we know this always has solutions? And the answer is yes, because the only thing that can go wrong is that there would be a row of zeros, but there's no row of zeros on the left-hand side. And that really doesn't depend on what we plug in here. And even if we started with a matrix that wasn't in reduced row echelon form, if we get to a place where there's no rows of zeros, then we know that there will always be solutions. Now here there are infinitely many, we have this free variable, but the idea is that checking whether there's a pivot in every row is really checking, when you solve the linear system, do you get a row of zeros? Because if you get a row of zeros, that means that some inputs are going to not correspond to outputs. Hopefully I said that well. Yeah, so if you get a row of zeros, you get that some, I said that wrong, that some output vectors don't have solutions, right? If you get, in this case, when we did this here, this is telling us, look, there's going to be some choice of initial vector such that after your row operations, this is inconsistent. And so this thing's not going to be onto. But here we didn't get a row of zeros. And so that's why we're checking that. So hopefully that gave you some insight into why this works out so nicely. It's really, the way I'm thinking about this is, it's really because these properties one-to-one and onto, when we're talking about linear, or when we're talking about any function, we're talking about how many solutions are there to an equation. And with linear transformations, we actually have really nice ways of understanding how many solutions there could be once we know the matrix of the linear transformation.